Angular momentum represents one of the most fundamental concepts in rotational motion. Just as linear momentum describes the motion of objects moving in straight lines, angular momentum describes the motion of objects that are rotating or spinning. Throughout this lesson, we'll explore how angular momentum works, how to calculate it, and why it's so important in understanding the physical world around us. Angular momentum is the rotational equivalent of linear momentum. While linear momentum measures how much motion a moving object has in a straight line, angular momentum measures how much motion a rotating object has. Think of a spinning top, a rotating wheel, or even planets orbiting the sun. All of these possess angular momentum. The faster something spins and the more mass it has distributed away from its center, the greater its angular momentum. The formula for angular momentum is L equals I omega. Here, L represents angular momentum, I represents the moment of inertia, and omega represents angular velocity. This simple equation tells us that angular momentum depends on two key factors: how the mass is distributed in the rotating object, and how fast that object is spinning. Understanding each component of this formula is crucial to mastering rotational dynamics. The moment of inertia, represented by the symbol I, measures how mass is distributed around the rotation axis. It essentially tells us how difficult it is to change an object's rotational motion, the resistance to rotational acceleration. An object with mass concentrated far from its axis of rotation has a larger moment of inertia than one with mass concentrated near the center. For example, a hollow cylinder has a greater moment of inertia than a solid cylinder of the same mass, because its mass is distributed farther from the center. Angular velocity, represented by the Greek letter omega, tells us the rate of rotation, essentially, how fast an object spins around its axis. It's measured in radians per second. One complete rotation equals 2 pi radians, so if a wheel completes one full turn every second, its angular velocity is 2 pi radians per second. The faster an object spins, the greater its angular velocity, and consequently, the greater its angular momentum. Angular momentum is not just a number. It's a vector quantity, which means it has both magnitude and direction. The direction of angular momentum is determined by the right-hand rule. If you curl the fingers of your right hand in the direction of rotation, your thumb points along the axis in the direction of the angular momentum vector. This directional property becomes especially important when analyzing complex rotational systems or when multiple rotating objects interact. One of the most powerful principles in physics is the conservation of angular momentum. This fundamental law governs everything from figure skaters executing spins to galaxies rotating in space. The conservation principle states that under certain conditions, angular momentum remains constant over time, meaning the total amount of rotational motion in a system doesn't change unless something external acts upon it. The conservation of angular momentum states that if no external torque acts on a system, the total angular momentum remains constant. In other words, without an outside twisting force, the product of moment of inertia and angular velocity stays the same. This means, if the moment of inertia decreases, the angular velocity must increase to keep the angular momentum constant, and vice versa. This principle explains many fascinating phenomena in nature and everyday life. Conservation of angular momentum appears throughout our world. When an ice skater pulls their arms inward during a spin, they reduce their moment of inertia, causing their angular velocity to increase dramatically. They spin much faster. Planets maintain their orbital motion around the sun due to conservation of angular momentum. Helicopter rotors generate lift through their rotation, with angular momentum keeping them stable. A diver tucking their body into a tight ball increases their rotation speed by decreasing their moment of inertia. All these examples demonstrate the same fundamental principle at work. Let's recap the essential concepts. Angular momentum, given by L equals I omega, combines mass distribution through moment of inertia and rotation rate through angular velocity. It's a vector quantity with direction determined by the right-hand rule, pointing along the rotation axis. Most importantly, conservation occurs when no external torque acts on the system. The total angular momentum remains constant. These principles form the foundation for understanding rotational motion in physics and engineering applications.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.